So today we're diving into a really interesting area, recommender systems. You know, those AI tools that help us sift through tons of information, especially now with all the multimodal content out there, like videos with images, sound, and text. But these systems often struggle with things like not having enough data, or what to do with new users or items, and they don't always make the most of the rich connections in that multimodal data. This paper proposes a new approach called Multi-Modal Hypergraph Contrastive Learning, or MMHCL, to tackle these exact problems. And it's great that the authors also shared their code for this work. So over on GitHub, you can find their PyTorch implementation for this Multi-Modal Hypergraph Contrastive Learning model, including the main model files, data preprocessing scripts, and instructions. Now, a core idea here is the hypergraph. A hypergraph is a special kind of graph where an edge, called a hyperedge, can connect more than two items at once, which is great for capturing complex group relationships. And this is combined with contrastive learning. Contrastive learning is a technique where the AI learns by comparing examples, essentially figuring out what makes similar items similar and different items different, to build better data representations. Okay, so this figure really lays out the architecture of the multimodal hypergraph contrastive learning model. We see two main hypergraph constructions. First, a user-to-user hypergraph, derived from user-item interactions. This uses hypergraph convolution, a method to aggregate information across these hypergraph connections, to generate rich user embeddings, which are essentially detailed numerical profiles for users. Then, there's an item-to-item hypergraph, built from the item's multimodal features. This also undergoes hypergraph convolution for item embeddings. These specialized hypergraph embeddings are then fused with standard ID embeddings from a recommendation model, and that synergistic contrastive learning we mentioned helps to further enhance all these representations. Alright, so after understanding that architecture with its user and item hypergraphs and the synergistic contrastive learning, this table, Table 4, really shows us the impact. It compares how well their multimodal hypergraph contrastive learning model performs against other methods on three datasets: TikTok, clothing, and sports. They use metrics like recall at 20, often shown as R at 20, which measures how many relevant items were in the top 20 suggestions, precision at 20, or P at 20, indicating the proportion of those top 20 that were relevant, and normalize discounted cumulative gain at 20, or NDCG at 20, which also factors in the ranking of relevant items. And as you can see, the multimodal hypergraph contrastive learning model, highlighted in bold, consistently outperforms all others. For instance, on TikTok, its recall at 20 improved by over 23% compared to strong baselines, which is quite a jump. This really underscores the effectiveness of its design. So we saw how multimodal hypergraph contrastive learning generally performs well. Now, Figure 3 specifically tackles the cold start problem. This is a common challenge where the system needs to make recommendations for new users or items, where there's very little past interaction data to go on. The chart shows recall at 20 for the clothing and sports datasets, and again, our multimodal hypergraph contrastive learning model, the purple bar, significantly outperforms the others. This suggests its ability to leverage those rich multimodal features, and the higher order connections from the hypergraphs is really beneficial in these data scarce scenarios. Okay, so building on its strong performance, especially in those cold start scenarios, Table 5 now digs into why the model is so effective. This is an ablation study, which is a common technique where researchers systematically remove individual components of their model to measure the contribution of each part. The table compares the full multimodal hypergraph contrastive learning model against versions missing either the user-to-user hypergraph, the item-to-item hypergraph, or the synergistic contrastive learning. And as you can see from the recall at 20 and normalized discounted cumulative gain at 20 scores across all three datasets, the complete model, shown in bold, consistently outperforms these stripped-down versions. This really highlights that every one of these components plays a crucial role. Alright, so that ablation study really hammered home the importance of each part of the multimodal hypergraph contrastive learning model. Now, Figure 8 explores the multimodal aspect a bit more deeply. It shows us the recall at 20 performance when using different types of item features, specifically acoustic, visual, textual, or all of them combined, which is the multimodal approach. Across all three datasets, TikTok, clothing, and sports, you can see the blue bar, representing the multimodal strategy, consistently achieves the highest recall at 20. This really shows that combining different types of information helps the model make better recommendations. It's also interesting to see that for TikTok, visual and acoustic features seem most influential individually, while for clothing and sports, textual data is more dominant. So considering all these findings, from the overall performance to the importance of each component and the benefits of multimodal data, it's clear that multimodal hypergraph contrastive learning is a really promising approach. It effectively tackles the challenge of making better recommendations by understanding complex connections and using rich, diverse information, especially for those difficult cold start scenarios. This research really pushes forward how we can build more nuanced and effective recommender systems. Well, that's all for this episode of the AI Research Roundup. Thanks for joining me. I'm Alex, and I'll see you next time.